All right. Well, thank you. Those, I guess, virtually. We got about a dozen online. Got 6 people here. Thank you for coming out. Our first attempt at like a hybrid talk from the CUNY MSDS. So, yeah, I'm excited to talk about propensity score analysis. So, has everybody here? You've all taken. I know you guys were my ML desk, but you also took 606 with me and Angela, right? Vanessa too, right? Yeah. No, you didn't?
No, I'm just taking this course as a matriculated student.
Oh, okay. All right. All right. Very cool. So I make some references. So you're actually going to see some duplicate slides that I do like in the first or second week when I talk about causality. But and for those online, I guess there's few enough. I could see the chat if you want to throw questions in the chat or raise your hand, and then you can unmute. We can actually hear you on this side. So we'll do that. And appreciation to Angela, who's co-hosting or kind of managing some of the back end stuff too. So if you have technical issues, just alert Angela. So thank you. So here's like kind of this seems like a lot. And in fact, we're not going to probably talk about the advanced topics. So this is sort of I'm going to do an abbreviated version of what I have taught as a 6-hour workshop, where if I do it as a workshop, there's a lot of pauses and you're going to do stuff. So I'm kind of just going to do some of the conceptual stuff and kind of go through it, and then point you to where you can get to resources if you actually want to run some of this yourself. So the first thing I want to talk about is this notion of causality kind of up front. So in 606, or you read the textbooks, right, the sort of classic definitions, if you want real causality, you need to do a randomized control trial. So we're going to start with, we're actually going to start with the Marvel multiverse and then get to randomized control trials to build a foundation for how this approach to doing causality with observational studies works. And then we'll talk about conceptually the 3 phases of PSA, and then some of the technical details in terms of doing it in R. And if we have a few moments, I like the advanced topics because these are things I've done, or sort of some of the advances I've made to PSA. So first of all, so PSA, propensity score analysis, and we'll define what that is growing in popularity. So this is some trend data going back. So the first paper on propensity score analysis was published in 1982. And you can see it didn't get a lot of traction initially until the late 1990s. And there were actually a couple of seminal papers after the first paper that really got it to catch on. And then it sort of has just exploded over the last decade or so. This red line here, so what I did is used Web of Science to find references for either propensity score analysis, propensity score matching as keywords in published articles. And then this purple line is Rosenbaum and Rubin, 1983, which is that paper using Google Scholar. So you can see it's kind of increasing. One of the reasons is I think it's a fairly compelling way of estimating causality in situations when you can't do a randomized control trial. So let's back up and actually talk about what causality is. So anybody who's taken our 606 class has probably seen this slide. So this is like my Marvel multiverse, right? So if we want to know what real causality is, we take some research subject, whether it's a student, a patient, a mouse, if you're doing mice experiments, right? And what you want to do is split the universe into 2 exactly same universes, right? Just like the Marvel world. And so what you do is you observe. The only thing different, right, is whether that observation, that individual, is going to go to universe A and universe B. Literally everything is the same except this condition, right? So time needs to be the same. All the environmental factors need to be the same. And then at the same exact point, at some point after you do that condition, you're going to measure the difference between that individual at the same time in universe A and universe B, right? That's a true causal effect, right? We call that a counterfactual. Now, of course, that is, this is not possible, right? Only in the Marvel world is that possible. So enter the randomized control trial. So what the randomized control trial says, well, what if we, at that split point, we just flip a coin and put half into environment A, half into environment B. Then on average, right, the difference between that observation here at this time point is going to be balanced, right? The reason why somebody went up to A and the reason why somebody went to B is 50-50, right? That 50% is going to be key. So, so that's what the randomized control does. And you know, statistically, what we're saying is we have a strong ignorability assumption, and that's key, right? And so some of my colleagues are online here. We're doing giant randomized control trials with our DAX project. And one of the things we have to do when we get all this data is we have to justify the strong ignorability assumption. One way we do it is we measure a lot of demographic data. Right, so we should not see any difference in the treatment assignment based upon things like sex and ethnicity and social economic status, right? And that's our way of justifying and saying, well, indeed, that randomization is, you know, balanced, right? That we can say the randomization assignment ignores all of the other observed covariates. So what we're saying is the outcome is independent of the treatment assignment. For all X, observed and unobserved. We observe some to check it, but we're assuming that it's going to be balanced on everything we don't see as well. So this is just some R code you can look at. So we're gonna, I'm just generating a simulation to get this plot. And so what I have here is I'm stipulating, so what I've done is on the X-axis is I have a distribution of scores with a mean of 100 and a standard deviation of 15. I picked that because IQ, a common measure of intelligence, is designed to have a mean of 100 and a standard deviation of 15. Each of these lines represents a single individual, right? And I'm saying I'm going to do some intervention such that after the intervention, that person's IQ should increase by 4.5 points. That's by stipulation, right? And so here's individual 30. If they were in the control group, this would be their score. If they were in the treatment group, their score would be 4.5. Now, the fact that they're spread here is that there's measurement error in IQ, right? There's a spread there. So that would be a true, right? I did the Marvel multiverse scene. And the average difference between all those is exactly 4.5. So far, so good. So what is an RCT? An RCT is, well, I only observe one of those observations. I'm only gonna, so for example, in the first person, they ended up in the treatment. So all I see is the red point. The second individual were assigned to the control. So I only see the control observation, so forth and so on. So what do I do in an RCT? Well, I take the average of the blue and the average of the red and compare the differences. When I do that in this particular scenario, it turns out the control is bigger than the treatment, right? So in this case, the RCT gave me the wrong answer, right? But everybody took 606, and they know from the central limit theorem that if we do lots and lots of randomized control trials, well, it balances, right? So this is doing, I think I did 1,000 randomized, simulated randomized control trials. You can see the red and the blue lines are the difference is right about 4.5, okay? But you know, right, so here's 0, a good portion of them have the effect in the wrong direction. My point is the RCT is already a compromise to the true causal effect. But if we can understand why the RCT is considered the gold standard, that will lead us into what's called Rubin's causal model. So this is theoretical framework, right? So here's our picture again, right? One of his students, Colin, referred to this as the fundamental problem of causality. We can only observe one of those two outcomes. The effect we're interested in, right, is the difference in the outcome. Y here's the outcome for subject I under the treatment condition, minus the outcome of that same individual given the control condition. That's not possible. So Rubin framed this, as a missing data problem, right? We observe one of these two outcomes, but not the other. So if we think about it as a way, as if we can compute the other value, then we can make those comparisons. So without going too much into the mathematical details, right? So what is a propensity score? It is the conditional probability of assignment to a particular treatment given a vector of covariates. I'm going to use the word covariates a lot. For those, we talk about predictive modeling a lot in this program. So covariates are simply our independent variables, right? And they should be variables associated with the treatment assignment, right? So if you're thinking about, well, what should I measure in these kinds of designs? I want to measure variables that are both predictive of why somebody might choose to be in the treatment or not, and are related to the outcome of interest. Because what we're going to try to do is adjust for those, so that when we make comparisons between like observations. Right? Okay, and if we do that, right, so Rosenbaum and Rubin defined, so propensity score here is represented as pi, given some set of covariates, is equivalent to the probability of the treatment being one given those assignments. Meaning, well, let me just state it this way. What they proved in that 1983 paper is that the propensity score, given all of these covariates, becomes a unidimensional simplification of the multivariate space. In other words, I can have, in the case of my dissertation, I had something like 40 covariates about how students are related to choosing to be in a charter school or traditional public school. I could take all 40 of those variables, estimate a propensity score, right, which is one number, and that is a simplification of all of those variables, such that if somebody has the same propensity score, they are very similar, if not exactly the same, in all 40 of those covariates, right? And that's what's key here, right? It becomes a univariate reduction of the multivariate space. And so then we can rewrite the ignorability assumption, right? So in the randomized control trial, we just said the outcome is independent of the treatment assignment. And what Rosenbaum and Rubin said, well, it's independent of the treatment given the propensity score. And we'll see how that plays out in just a moment. Does that make sense so far? I think as we go through the example, hopefully it makes a little more sense. Okay, right, and so what's a treatment effect then? Well, it's the expected value given the treatment minus the control, just two expected values. So when we rewrite it for a propensity score, right, this is just for the randomized control trial, although we could represent the randomized control trial this way, and we just assume everybody has a propensity score of 0.5, right? We just flipped a coin, everybody has the same probability. So all we're going to do is now say the average treatment effect is going to be the difference in the outcomes given this matrix, and we're going to adjust for that. All right. So how are we doing online? Any questions there? Great. All right, so what I'm going to do here is simulate a data set to kind of demonstrate this. So I could fix everything to look at it, and then we'll look at a real example. So I'm going to have two covariates, x1 and x2, that are continuous, and then a third covariate that is dichotomized. And so I'm just using the random multivariate norm package to generate that, so you can kind of get a sense of the variables. So I have x1, x2, x3, a treatment, which is 0, 1, and then some outcome. And you can see here, I fixed the treatment effect at 1.5. And we can play with that in a minute. And this is what the data look like, right? So right away, you might look at this and say, well, people who are in the treatment are going to do better than those in the control, right? But that's kind of just on average. So what we want to do is adjust for these variables. So the colors of the treatment assignment, sorry, you probably can't see, but there's triangles and then there's circles for that covariate, that categorical variable. Right? But we don't have any outcome here. So we don't know that, right? We just see this trend, right? That how these variables relate. Oops. Okay. So there's three major approaches to doing PSA. There's what's called stratification. And this is what we're going to do is after we estimate the propensity scores, we're going to create little groups. Or we can use a classification tree. And the leaves of the classification tree would define each strata. We could do matching. This is often a little bit more natural to think about. So what we're going to do is say, well, here's a treatment observation. Let me find a control observation that looks as close to this treatment observation on all the variables I've measured. And then we'll make a comparison there. Right, so what ends up here is stratification. We do independent sample t-tests. We'll do dependent sample t-tests. And then weighting is we're going to use the propensity scores as a regression. So if you want to do something more complicated, like a multi-level model, maybe a time series model, you could potentially, there's some papers on using propensity score weights in time series models, for example. All right. So what does that look like? So here in this plot, I have the distribution propensity. I should say, I'll show the details on how I estimate it, but here what I did is just ran a very basic logistic regression with 3 predictor variables, x1, x2, x3, predicting treatment. And so the x-axis here is that propensity score, which is simply the fitted values from the logistic regression. That's all it is here. And so we have the distribution, distribution for the controlled observations and the distribution for the treatment. And so as somebody who does this type of analysis a lot, this looks pretty good to me. What I see is separation between treatment and control. Obviously, if I'm predicting treatment well, right, then the treatment distribution should be skewed to the right. If I'm predicting control right, it should be there. What I want to exploit is this overlap, right? So I have some treatment students who had a very likelihood of being in the treatment, but we're still there. I'm going to compare to them controls. Similarly, I have some observations, some control units that I predict wouldn't be in the control. I would predict to be in the treatment, but actually we're in the control, right? And as we'll see, these end up being very, very similar. So in a stratification approach, what I'm going to do is say, well, I'm going to take all the observations in stratum A, compare them, stratum B, compare them, C, D, E. So in this example, I use 5 strata, and this is based upon work by Cohen in the 60s, if you can believe it, who showed that having 5 strata, or using stratifications with 5, reduces the bias by approximately 90%. So you can go to more, and I'll show you can do 10. I go usually, if I have a very large sample size, I'll go as high as 10. But going more than 10 doesn't really give you a whole lot of additional power or benefit. And then this is what it looks like with the outcome. So all I did here, so here I have the propensity scores and the distributions. Now I've put on the y-axis my outcome of interest, okay? So I have in stratum A, here's my mean for the control, here's my mean for the treatment. And I have a standard error bar there just for reference. So there are methods to do this. So there's some, I hesitate about having these error bars. I think they're useful. We're not typically doing a multiple comparison test. If we are, and you want to make inferences about each individual stratum, you should probably do something like a Bonferroni adjustment. But what we're going to end up doing is just pooling the effects or the differences across each stratum to provide an overall effect size. So that would be stratification. Here, the strata are defined by propensity scores. I use quintiles here, right? So the number of observations in each bin is the same. If I wanted to use a classification tree, then I would use like the leaves of each tree or each node as the points of comparison, where I would probably have a few treatments and then more control or vice versa, right? If it's a good classification tree. Now for matching, this is a little messy and it's probably a little washed out for those in the room. But what we have here is we'll talk about matching algorithms. So just trust me that I found a map. One way you can think of it is I just want to find the nearest neighbor. So we can see here, for example, here's a control unit. That's control. Yeah. And it was matched to a treatment unit somewhere that I can't see. Oh, right here. Right. So these two, and you can see the key point I want you to take away from here is all of these matched pairs, these lines are fairly vertical, or pretty close to vertical, because the propensity scores are very, very close, right? And as we'll see, that means they're probably very, very similar on what we observed. And so when I do that, I would just then do a dependent sample t-test, because I have matched pairs, and I would just do a difference. So to get this line, so what I ended up doing to kind of extend this visualization, this line here is the lowest regression line fitting the differences between the matched pairs with a 95% confidence interval. And so then this horizontal line at 0 is essentially our null hypothesis, right? Our null hypothesis is that the difference between the matched pairs is 0. So the fact that it doesn't overlap, right? And I mean, it wiggles a little bit because there's some random noise in there, but it's roughly at 1.5, which is where I stipulated my treatment effect should be. So a lot of matching procedures. I'm not going to go into detail. I'll point you to references. But the main takeaway is which one do you use? This is the one that gives you the best balance. And we'll come back to balance in a second. So weighting, to understand what weighting is doing, so we're using an inverse probability weighting technically. So I'm still using propensity scores as fitted values from a logistic regression. But now the points are weighted by that propensity score such that control units on the high end of the propensity score range are going to count more than the ones on the low end. And conversely, treatment units on the low end of the propensity score range are going to count more than the ones on the upper range. So you can kind of see the points, the green points get smaller as you go from left to right, the orange points get bigger as you go left to right. And that's kind of what weighting does. And so this is a lowest regression line using those as weights. And again, similarly, I took the horizontal line at y equals 0 because that's our null hypothesis. And so the line doesn't expand it anywhere along the line. All right, so if you want to play around with this a little bit more, I have a package called PSA. You can do some things here. But the main thing I'm going to really show right now is the treatment effect. So if we look at something like stratification, right? So what does it look like as I make the treatment effect get smaller? Right? Of course, they're getting closer to the point where we still get some noise here, but probably in aggregate where we have 3 strata that overlap, 2 that have a little bit of a gap. If we go to matching, right? You can see here now the lowest regression line is the 95 confidence interval spanning across almost everything. But of course, if I increase it, then we start to see the difference. And then similarly for weighting, right? So if you have no effect, you're going to see a lot of overlap. So you can play around with this. You can change some other things like which estimate we're going to look at, but we haven't talked about that yet. All right, questions about like the 3 major approaches to doing this. Cool. All right. So this is from Stewart and Robin. I tend to think of propensity score analysis in 3 phases, which kind of, I combine some of these things, but this gives you a few more details. So first, if you can, choose the covariates that you're going to use. Now, I have in the past designed studies that I knew were going to be analyzed using propensity score analysis. Like we want to study this. Like for example, I studied the effects of tutoring in online classes. We couldn't randomize students to tutoring or not. It was made available to everyone. So we said, okay, well, we can't do anything about that. But what we can do is make sure we gather enough information about the students so that we can hopefully successfully predict or model them choosing to use the treatment or not. For example, one thing we found out, women are much more likely to use tutoring services than men, right? Or males. And that's kind of maybe true in general, right? But the goal is, you probably know your field in education. We have a set of variables that we know are generally related to various academic outcomes or whether or not someone's going to use or choose to use some type of treatment. Now, a lot of times you're just going to use a pre-existing data set. And so you got what you have. And so at the end, we'll talk about, well, how can I test what my effects or my estimates to an unobserved covariate. So that's something to be in mind. So if you can, just measure as much as you can that you think is relevant. Now they were talking about the context of matching. So, they're talking about defining a distance measure, and we'll look at that in just a moment, get to matching. But you're also going to talk about method. And generally my rule of thumb is you're gonna try multiple distance measures, and you're gonna try multiple matching algorithms to find the one that gives you the best balance. Then you're gonna observe the balance, and you're gonna essentially iterate through steps 2 and 3 until you get sufficient balance. And then finally, will you make an estimate? All right, so let's look at some of the art details. So this is probably very familiar, right? I'm just running a typical logistic regression with my 3 predictor variables, right? It's using the binomial family. And then the propensity scores are just fitted values. That's all it is. Right. Now, I have a utility function that will stratify for me the propensity scores in the 5. There's a whole bunch of, it actually gives you a data frame, so there's a lot of interesting stuff in there, but really all I want to do is get the breaks. And so I'm cutting the propensity scores, in this case into 5 straight up. If you're interested, right, because this is from the simulation, all the predictors are significant predictors of treatment placement. That's kind of by design. When we look at a real world example, it might not always be that case. Right, and again, this is just a slightly different view of the propensity scores. All right, checking balance. So this is one way. So this is a package I just inherited as a maintainer, but it was written by my dissertation chair of PSA graphics. And so we have the way this is set up is we have our covariates on the y-axis. Then for each covariate, we're going to estimate the treatment, the effect size of that treatment. Of that covariate on the treatment before and after adjustment. So the red line is the effect of, so X2, X1, X3 on treatment before we do anything, right? They're all very significant. The effect sizes are larger than 1, quite large. So what we do in this case, we stratify, right? And then, so we have strata A through E, right? And then this blue dot is the average of the absolute value of the effect sizes for each stratum, right? So remember, we stratified. So I'm going to take stratum A, which is just all the individuals that fall on the lower end, and look at the effect of that covariate on treatment within that, right? And so they all are lower. And then I take the average across, in this case, 5 strata. And so the effect sizes are all small, right? This is what we're hoping to see. We've taken the effect of that covariate and made it really small for each of the individual kind of strata that we're actually making the comparison. So this is a nice plot because you see everything all at once. Now, the literature doesn't give you a lot of guidance as to what is small enough. Sort of my general rule of thumb is I tend to want effect sizes after adjustment to be under 0.1, right? Which is about 1% of variance accounted. So that's kind of what I'm looking for. And sometimes I'll put a vertical line to kind of see that. But what I might do is go and actually look at individual covariates. Okay. So on the left is for what we look at for a continuous variable, which is just a bunch of box plots. So here's stratum A, right? And so we have box and whisker, and we're connecting the means. So the means of that group are pretty similar. Spreads are pretty similar. And of course, because the way I designed this is we go from left to right, right? Those in the higher strata have higher means in that covariate. For a continuous, categorical variable, we'll use a stacked bar plot, right? So if, for example, if somebody was false, was a false outcome, this is a simulated data set, so it doesn't really make it. If you think of this like male, female, right? So maybe it was female, male, right? The way I would look at this, like, well, then females are more likely to be in stratum, D and E kind of split here, right? More like this. So think about it. So when we're making the comparison, they're very similar in that characteristic. And that's kind of what's key here and then why this works out. All right, so where are we at time? Okay, I think this is kind of an interesting way to look at treatment effects. So when we do randomized control trials, we only ever report what's called the average treatment effect, right? And I defined that earlier. What's the average treatment effect in an RCT? It's the mean of those in the treatment condition minus the mean of those in the control condition. But because the distribution across the propensity score, I mean, that works because if I were to draw a histogram of an RCT, I would just have one bar here in the middle, right? They would all be in the middle because they all have a propensity score of 0.5. But now I have a range. And so we kind of saw this a little bit in the weighting, right? When we looked at weighting plot, the points for treatment conditions were smaller on the right side than they were on the left side. And conversely, the control units were larger on the right side than they were on the left side. Right? Why is that? Well, because if I'm taking those, if you think about when I'm creating those strategies, like if I'm here, I'm just comparing all of these individuals, for which there are many more treatment, to the few controls I actually see up here. That's the comparison I'm making. So when I report an average treatment effect under this kind of condition, right, I'm actually weighting these control units more. And so the kind of darker color is the actual observed distribution. The kind of full color bars is the effect after the weighting, right? So in order to get this to match this, because I want the distributions to match, I'm going to weight up these observations, these control observations. And then down here, right, I'm weighting up these treatment units that happen to fall on the low end of the propensity score range. Right. So the point being is an average treatment effect under this regime means that not all observations are counted equal. And that is an important thing to take note of. So because of that, there are alternative treatment effects that you can report. And probably one of the more common ones is the average treatment on the treated. Because really, oftentimes what we're interested in is what is the effect of the treatment on people who actually receive the treatment, right? And for whatever reason, people on the low end of the propensity score aren't getting it. But what we really want to know is those who get it. So you can see in that case, right, on the right side, we're still weighting up those control units. But what we're going to do is we're going to drop, or we're going to downweight. So the gray bar represents here control units that aren't actually really counting that much or at all into the treatment effect. Okay. So of course, if we have, and just formulaic, right? So a lot of this is we're changing in the expected value here, right? So we're still conditioning on the covariates, but only if the control is 1, meaning that they're assigned to the treatment. We could reverse it and say, well, we can estimate the average treatment on the control. Right. So now we have a bunch of treatments we're not using. This could be interesting in different contexts, right? This is the effect of an intervention for people who are less likely to choose the intervention, right? And some of my colleagues, maybe they can chime in who are online on the tax team. We kind of see this a little bit in our data that the students who most benefit for the intervention are the students who choose not to show up for the intervention. Right. So a lot of times what we're trying to do is find ways to incentivize them to participate in the intervention. Right. And we've tried things like nudges and other kinds of things to try to get that. But this could be an interesting estimate in that case, right? Because there's a lot of things going on here. And one of the things I love about propensity score analysis is it's not presuming that the treatment effect is homogeneous, meaning it's not the same for everyone. And so when we start running propensity score analyses to estimate causal effects, even under randomized control trials, what we start to find is that the intervention is not the same for everyone. And through those balance plots, we can start to tease out who the intervention is more effective for. And when we go through a real example, we'll see that. This is another one. This is average treatment among the evenly matched. So if we're doing matched analysis, where we're matching people up, this is sort of a weighting counterpart to that. And at the end, I'll point to some references if you're interested in. But the key here is we're kind of emphasizing points in the middle, right? So we're kind of taking out the extremes from the treatment and control side. Here's a lot of math. I think most of you would rather see our code. So in the PSA package, I have a function that calculates those treatment effects, which just essentially implements these formulas for you. But what's kind of cool, right? So here's the average treatment effect on using those weights. And so I get 1.33, not quite the 1.5 I designed. Some of this is a little off because I dichotomized one of the variables, so I'm never going to quite get back to 1.5. But here I'm doing just a plain OLS regression, outcome modeled from treatment, bivariate regression at that, with my data. And here's where I specify the weights. And the slope is exactly the same. So if I use the average treatment among the treated, right, I get 1.44, get 1.44 if I use it as a weight. So this becomes really, really, really nice because you can then adjust for the selection bias, but then run it through a multiple regression if you want. Or like I said, or a mixed effects model if you want, if you have some kind of hierarchy in your data. These are just the other ones, same kind of answer. All right, let's walk through examples. So the classic example to talk about propensity score analysis is what's called the Lalonde data set. So this is from an author, Lalonde. I think he published this in like 1980. And there was this program in the 70s called the National Sport Work Demonstration. And its goal was to, I think mostly males, or this data set is only males, it's a subset. What was neat about it is there was both self-selection and randomization done. So it became a good test case to test whether or not PSA gave you the same answer as a randomized control trial. Okay, spoiler alert, it does. And there's actually been a number of other RCTs where what they did is randomized groups in the educational context. They did this where they randomized people to two groups, families to two groups. In group one, they randomized people to an intervention or not. In group B, they let the families decide whether or not they wanted to be in the treatment condition. So to me, it's kind of mind-boggling, the design here. And the effect that they got from the group, from doing the randomized control trial and from the group that they let self-select, they did the propensity score adjustment, ended up being statistically equivalent, right? And there's been a couple of studies. So this is the first, so this is in the 70s. Rosenbaum and Rubin wrote the first paper in 83. And and then later on, Lalonde collected this data and it became an interesting, and everybody uses it to demonstrate PSA. It's not my favorite, but it's sort of the classic. But the goal was participants were initially randomly selected. This ended up being an observational subset, and they had a whole bunch of covariates, and including real earnings in 74 and 75, whether or not they had a high school degree, whether or not they were married, et cetera, et cetera. We'll look at all those variables. And what they wanted to look at is the difference in income in 1978. So they put this in this work program in order to try to get them increased pay or employment. Okay. Make sense? And from the randomized control trial, I think the effects were somewhere between 7,000 and 1,600. That's a pretty large range. It's usually because there's some skewness here in outcomes. So usually somewhere around $2,000. So from 1975 to 1978, they generally found people made $2,000 more if they participated in this work program. 70s, $2,000 is a lot of money in the 70s. Might not be as much now, but. Okay, so it's in the Lalonde data set. So let's just dig right into it. Again, right, and I know I say this in 606, right? So much of, we talk a lot about statistical procedures, but so much of this works because of design, right? There's not a lot of fancy statistical models going on here. Just doing a regression, right? So I have age, education level, whether or not they're Black or Hispanic, whether or not they're married, This one drives me nuts. So no degree. So it's 1 if they don't have a high school degree. So you gotta just remember that if you want to interpret coefficients. And their earnings in 1974 and 1975. My dependent variable here, step 1, phase 1, is treatment. So I run a logistic regression, I get the propensity scores, and I'm going to define 5 straight at here. So we can see here, well, what are the big predictors? No degree, right? Not having a degree has an impact such that, so it's negative. So I see now I can't think of, I almost want to reverse it so I can interpret it, right? So so I think it means people who didn't have a degree are more likely to participate, maybe because they had more time. And then Hispanics were less likely to participate. Now, a couple of things to say, because a big question in the literature is about variable selection. I think we talk about this a little bit when we talk about predictive modeling. I'd like to hear what you have to say when you learn later in classes. Just a bit more. In propensity score analysis, generally, we don't use 0.05 or 0.1 as a threshold. I have seen some people say 0.5 is a threshold. If you have a lot of covariates, right, you don't necessarily want to have them all. Like in my dissertation work, I had like 40. So I reduced it down, but I used 0.5 as my threshold in terms of p-value. So I'd account for at least, the p-value had to be at least 0.5. But you're probably better off leaving it in than taking it out, because anything that could give information to your dependent variable, we're generally not interpreting these coefficients, right? We just want it to get the propensity score. So just be aware of that. So I'm going to leave them all in and just kind of move on. All right, first thing I do is check my balance, and I like this plot to begin, and then I dig in from there. Right, so you can see that no degree, right, which is probably not a surprise. It was a strong predictor in the logistic regression. So after I do the stratification, right, so here's my 0.1. So that's often what I look for, is like all the blue points are to the left of that. So I'm feeling in pretty good shape. I'm going to show a shiny app where we can do some stuff to maybe get a little bit better. But in the grand scheme of things, to me, this is a great start, right? The model is doing a pretty decent job of adjusting for the selection bias. We could start digging in the individual variables. So here we have age, right? Age wasn't big. Earnings is kind of interesting, right? Because again, if we're going to talk about heterogeneous treatment effects, this is where things kind of get interesting, right? So I want to look at the effect for stratum B and C, where like the mean is almost 0 in terms of real earnings, right? So I could look at the effects in just individual strata if I want. But you could start to build profiles, right? So here, education level, right? So people who are of higher education were more likely to choose to be in the treatment. Maybe not a surprise, but good to see that kind of play out. And in this case, right, this is interesting because the other ones are, across all of them are the same, right? This is really the kind of differentiating factor to get into stratum E. Not a lot to say in real earning 75. We see a little bit more here. So Hispanic. So the 1 is no, right? So if you're not Hispanic, you're probably in stratum A. Right. So these are the kinds of things we can see. No degree. So the 1 is no. So yeah, right. So if you had a degree, you were likely to enroll into this intervention, right? Those who didn't have a degree didn't enroll, right? All right, so this is, so after I do that, like balance is okay, right? I feel like my comparisons are going to be okay. This is one I don't think I really looked at yet. So I talked about 3, right? We could do stratification, we could do matching, and we could do weighting. In this case, I'm just going to plot things almost in the raw format. Now, I didn't include the points because there were so many, it just got cluttered. So these are 2 lowest regression lines for treatment and control, right? With, in this case, these are 68% confidence intervals because I want to compare overlap. And I have a reference if you care about that later. And so the fact that they don't, right, so we can see the treatment is really effective for folks in this range of propensity scores, maybe a little bit less on the lower. I also get the distribution propensity score at the top, and then the unadjusted distribution on the side. So if you tilt your head to the right, you can kind of see what we would conclude, which is probably nothing if we didn't do any adjustment. So I can look at my stratification, and here I showed 5 and 10, right? So again, we see sort of on the higher end of the propensity score, that's kind of driving where the effects are. These plots are really neat. So what I've done here is take each of the strata, right, and plot them so that I'm plotting the average score of the control for each strata to the treatment. Okay. Now this blue line, so this is the unit line. Some of you may have seen this. I don't always talk about this in 606, right? So this is the unit line, y equals x. So if a point falls on the line y equals x, that means y minus x is 0. So there's no difference. This line is perpendicular to it, right? Such that if I take all these and project them down, what we have here is a distribution of difference scores. And then this is a 95% confidence interval. This confidence interval does not span the line y equals x. So I would have a statistically significant effect. See the same thing if I use 10. This is just a summary statistics. You can look at that later. So here I could do matching. In this case, I'm doing one-to-one matching, and the default is to use the average treatment of the treated. So I'm going to leave that. A little bit harder to, I'll show a picture on the next one, right? So we see our effect size is 2579, which is in the ballpark of what the randomized control trial had, and it is statistically significant. But because we're doing a dependent sample test, so if you've taken the class, I think I showed this in the last year, I added this to the slide deck. Same thing, except each point here is a matched pair. So I took a treatment observation, matched it to a control observation, so I'm just plotting those points. Same thing, if I take all these points down to a line perpendicular to line y equals x, this is the distribution of difference scores, ends up being a lot of matched pairs here. So this little blue bar is the confidence interval, and this green line is the mean difference. The key is that that blue line doesn't span the line y equals x. We have a statistically significant effect. This is an alternative to balance and matching that I'm going to skip. Oh, well, I do want to show something real quick. Right. So this panel is every matched pair. So every vertical line represents a matched pair. If it's colored, right, so then what we have is no degree, education, black, real learning 74, 75, Hispanic, age, and marriage. So I have an a pair here. If it's highlighted, that means I did not match exactly in that covariate. So you can see over here for, well, we got 68. So I guess that would be for 32% of the matched pairs, they matched on either all or all but one covariate. Okay. But I have some over here. It's hard to see. I think 8%, right? It really didn't match on much, right? And so they're kind of all clustered over here. The other thing I could see is like education, right? Is a big one that's not matched. But then what I put up here is, well, I got a couple things. I have a relative importance factor. How important is that covariate to modeling treatment? And then the effect in aggregate overall, right? So I know no degree, right, was a significant predictor. I saw that in my logistic regression. I saw it a few other places. I have a bunch, and actually in aggregate, I don't have I would reject null hypothesis. Still has a significant effect. So under matching, what I can do is say, well, when I do a match exactly on no degree variable, and then get as close as you can on the propensity score for the rest. Right. So now notice this is 0. I have perfect balance on the no degree variable. So now there's obviously no confidence interval because they exact matchly. And so I can improve the overall balance by selecting a couple of variables to kind of match exactly on. So that could be really important. Sometimes you do it because the data suggests you do it. Sometimes you do it because theory tells you should do it, right? So we know in education, right, there's certain covariates that like socioeconomic status, right? I really want to make sure I adjust for that. Even if it's not a statistically significant predictor of treatment, we could still do that. All right. I'm gonna wrap up in 7 minutes and take lots of questions if you have them. All I'm gonna say, there's a lot of details here. I'm gonna go right to the R code. So sensitivity analysis asks the question, great, you have a treatment effect, you've demonstrated you have decent balance in what you observed. But what if I give you this new variable, right? You didn't even measure it. You don't know what it is. And it can explain more variance in your treatment indicator, right? It's going to be an additional predictor. So sensitivity asks the question, what is the magnitude that variable has to have to change the treatment assignment before I change my answer in my treatment, before I fail to reject the null hypothesis. So I'm presuming we're rejecting the null hypothesis. So like what's the factor that variable has to have before I no longer reject the null hypothesis? Okay, and so it just iterates through. And so so there's this thing called gamma, right? That's gamma is simply the magnitude of that factor. And so here, this is from the Lalonde data set. So I'm looking at, right, of course, 1, right? So I have the lower bound of the confidence interval and the upper bound. Well, this is just where I started, right? Or factor of 1. Well, what if it explains 10% more variance in my treatment indicator? Well, now my lower bound is almost always going to be 0. So really what I'm looking for is the upper bound. So the upper bound of my p-value is 0.0016. Okay, I'd still fail to reject. I would still reject the null hypothesis. What if it's 1.2 times larger? 0.0069. I'd still reject. Then I get to 1.3 factor. Now I'm at 0.02, right? But now I get to 1.4, right? So I have one more variable that has a multiplier 1.4 and increasing, predicting the treatment indication. Well, if I have that, now the upper bound of my p-value is greater than 0.05. I would no longer reject the null hypothesis, right? So that's the magnitude. So in education, I know we see things like between factors of 1.3, 1.5, that's good. Now I've seen studies looking at smoking, right? The literature on smoking. Those are the largest. Like you would have to have variables that are like 6 or 7 times, would have to have an impact on your treatment placement by 6 or 7 times, meaning the effects of smoking is so compelling, even though we've never done a randomized control trial to look at the effects of smoking. I think the evidence is pretty clear because when you account for all of the predictors, whether it's socioeconomic status, gender, ethnicity, sex, whatever, we can really account for that. And the effects of smoking are so strong that to counteract that selection bias is pretty large, right? So you need to know your literature, what that magnitude is, but this doesn't, all it has said is, first of all, that's presuming another variable exists. You have a well-designed study, right? You're going to say, well, what's the likelihood of something else coming about? That's the first assumption for doing this. But it gives you a sense of how confident you should be in that conclusion to an unobserved variable, right? That is the beauty of the randomized control trial, because we're balanced for everything observed and not observed by doing that coin flip. We know it's 50-50 to be in the treatment. Now, so unfortunately, sensitivity analysis is only really well defined for matching methods. And so Rosenbaum in 2012 proposed, well, you could test the hypothesis more than once. Not only does it help with, at least some sense of testing for sensitivity to unobserved confounders, but it also allows you to test for the sensitivity to model choice, right? And so this is one area where I've extended it. So we talked about bootstrapping in 606. I'm not going to talk about the details about that, but what I did is wrote a package called PSA Boot, which kind of takes the notion of bootstrapping, but applies it specifically to propensity score methods. So first thing I do is I draw bootstrap samples separately for treatment control, right? So if I have 50 treatment and 100 control, right? So a total sample size of 150. For each bootstrap sample, I want to make sure I have 50 treatment and 100 control. I don't want that ratio to change. So I draw a random sample replacement from treatment of 50 and a random sample of control of 100. So my total bootstrap sample is still 150, but the ratio of treatment and control is the same. Make sense? But the notion is the same, right? I'm sampling with replacement. For each of those bootstrap samples, I then estimate the treatment effect and balance statistics using a whole bunch of propensity score methods. By default, out of the box, it does 5, but it's easily extendable. And so I do that, and then I estimate the treatment effects, and then I get the overall treatment effect the same way I do any other bootstrap sample. I just look at the distribution of estimates. So this is the R code. This gets really long, so you don't see much. So this is the Milan, so you can see. So here's stratification results with the. So I give you the estimate if I just didn't do bootstrapping. That's essentially what that is. And then the bootstrap estimate, the bootstrap weighted pooled estimate. The weighted pool means I weighted on balance. So some bootstrap samples are going to have better balance than others. This is going to weight those that with better balance higher than those with less balance, et cetera, et cetera. Instead of looking at a table, we can look at a distribution. So here's a distribution of the effects using the C tree. This is the party package, so this is classification tree. Matching using the matching package, the match it package. RPart, which I recommend don't ever use. RPart is not the best classification method, but it's built in R, so I use it. And then stratification. Oh, these are balanced, right? P is right. So here is the unadjusted, and then the black line I think is the pooled, and then the blue is the balance without bootstrapping. We can look at all the bootstrap samples. I'll skip over that, and then right, this is the ultimate where you can see. I mean, Lalonde is, we saw the kind of sensitivity set, 1.4 or 1.3, I can't remember where it was, but there's a lot of variability. So we see, our part, you take that out. But the matching has some difficulty, the confidence span's a little bit wider. But you could just estimate this off and use that. It actually turns out to be fairly close to what we would do without anything. And we can look at the relative performance. This is where I start to see, our part, its correlation with the other methods is pretty low. So it's so if you're ever doing classification trees in other contexts, just don't use our part. C tree and party is quite good. Random forest, of course. So I'm going to skip over all this because we just don't have time. So last thing I want to show is, so the R code is available if you want to use that. This browser. So there's a shiny app, the PSA package. Let's go to the Lalonde since that's what we've been talking about. So there's some built-in data sets. However, you don't want to program everything out. You can just upload your own data set and select your variables, and it will go through everything. So you can look at your propensity score estimates here using a logistic regression. You can look at your balance, and this is where I like it a lot. So so we could choose the number of strata here, so we can go to 10 if we wish. But this is where you can play around. I like this interactively to kind of figure some of this out. So I could say, well, I definitely want to match on no degree. Okay, where am I at last? So I have Hispanic, but then I also have real earnings 74. So maybe I could do that. But what you might not be able to see here, the other thing you need to be careful when you're doing matching is I have further constraints on what can be matched. My sample size might get smaller. I might use fewer observations. So there's sort of a delicate balance that you got to do there. The nice thing about weighting and stratification is you use all your observations all the time, and matching, sometimes you're making choices of which observations you may drop. And then you could go through, you could look at matching results and the way that we already talked about. Oops, broke that today, evidently. And there's stratification results, and if you want to look at the data. So kind of a nice way to kind of view and run some of the PSA in an interactive way. That sort of is a crash course in propensity score analysis, and I'll happily take any questions that folks might have here or online. And I think you guys can mute online if you want to ask a question. We can hear you here. If you want to know more from the I think from the email I sent out, or you can just remember this, it's psa.briar.org. I'm in the early phases of putting all this down into sort of a book down site. The introduction chapter is mostly complete, I would say. It needs a little bit of editing. I'm working on the weighting chapter next. I'm not going in chronological order, but every section I think has R code that you can look at to run through it. So you can always feel free to email me and ask me afterwards. You say, oh, I have a data set I want to try this on. You can try to replicate it as you go through. But a lot of what I covered is basically I just talked about what's in chapter 1 for the most part here. So you have written notes for all of that there, and kind of writing it. So you can see a lot of the same figures. And it's all in GitHub, of course, including the package. And there's some notes here on how to create some of those plots if you want to do that. And I think everybody else knows how to get a hold of me through email.
Question?
Yeah.
Okay, so one of the first slides that you showed was density scores, the popularity was trending up. As it tells a different story from randomized controlled trials.
Yeah.
I'm not sure quite what kind of a different story it tells.
Then randomize, well, first of all, allows you to try to get causal estimates in situations where you cannot randomize.
Okay.
So that's key. And economists have been doing this.
Have data where something's already done and you're kind of coming after the fact.
Yeah, or if it's just not feasible, take the smoking example, right? It's not ethical to randomize people and say, hey, you're going to start smoking and you're not going to start smoking, so we can decide the effects of, smoking. Right? So in my world, in the education world, so charter schools is another classic, right? I mean, charter schools are by definition schools of choice. And so to randomize people, is difficult. Now, Stephen Levitt, and some of his colleagues, he talks about this in the Freakonomics book, looked at the effects of magnet schools, again, because it was about choice, but what he took it, he was able to exploit it in a different way. And I think people have done it with PSA afterwards, but what he ended up doing is looking at only people who applied to go to the magnet school, and because it was a lottery, he looked at the outcomes for those who ended up going and those who didn't, based upon who applied, right? So there were other ways to adjust for. Now, it just turned out knowing whether or not somebody applied is a strong predictor of being in the treatment, right? And that's another way you can handle it. So I don't have slides. I worked on Head Start many years ago. We saw, we were evaluating the effects of 2 years of Head Start versus 1 year of Head Start. Okay, now there are a lot of reasons why somebody, kids might enter Head Start third grade. Often it's higher needs, but sometimes it's just families, knowing to seek out those services earlier than others, right? And this actually goes to a fundamental question in sort of developmental psychology. Without going down the rabbit hole, there's somebody like Piaget who had talked about these stages of development. And, he would theorize, or Piagetians would theorize that 3-year-olds are not cognitively ready to engage in the academic activities that are done in Head Start. So you should not see any benefit from having 3-year-olds in school. They will just get it as 4-year-olds because they're just not ready. Okay, so it turns out that's not true. First of all, Piaget was wrong. He was right. I think in some ways he's right, but his age levels are wrong. But the other thing we saw that was of interest is that when we did the stratification, there was always this one stratum that wasn't really responding to the intervention. In other words, they weren't responding to the extra year. And it wasn't until we started digging into the balance plots and we realized there were a couple of things, but the biggest one is one of the biggest indicators that would put somebody in that strata was the social economic system. Now, by definition, all these people are below the poverty line, right? But these families were sort of on the cusp of being above, right? And, in talking to the director, right, we were able to kind of gather some more information because she knew who these families were. Well, at the time, I don't, that's all gone now, but she'd say, oh yeah, they're working really hard. They're a hardworking family. They're at this level because of other circumstances. They're really involved in the school, right? So, and that's a case where, boy, we wish we had measured those variables. That's where, we could have selected whether or not they got it. But the point being, like, Head Start's really effective for people who really, really need it, right? And in other words, the effect wasn't as good because they had the supports at home, right? And so, of course, the intervention wasn't going to work very well for them because they didn't need it. They were getting the supports at home. So that's another case, right? So this notion that treatment effects are the same for everyone, this is one way to tease it out. In the medical world, I see PSA used a lot to detect violations in randomized control trials, because there's this sort of known effect that phenomenon where doctors tend to have patients they like better than others. And so they have ways of ensuring their favorite patients end up in the new drug study, right? And so that's really a problem. And so people use PSA to say, oh, what's going on here? There's, we can detect violations of the randomization procedure. So it can be used in that context too. Other questions? That's a good one. No? Anything online? Going once.
Well, I would ask a general question.
Yeah, sure.
I would just say I would naturally start with math before all the other types of. And you talk a lot about this. Like if I'm in most situations, I don't really get a lot of sign. I'm really kind of limited by the data. I'm already limited of whatever I have access to. Although now with things like cell phones essentially always listening in on everything, it's pretty much have your pick of the litter. Is that part of the reason why maybe PSA is coming? Or maybe you guys really design some really neat stuff. If you have a custom app, you give this to people to maybe treat or trying some health treatment or some other thing. I'm not sure what I'm asking, but maybe we're in an age where we have so much data that we can actually design really nice experiments.
Well, so that's where it's funny, like in the right, because in the data science world, I hear about, in Silicon Valley, they A/B test everything, right? Google A/B tested shades of colors of links, to absurd levels, in my view. And that's fine if you can do that. That's great. But I think there's also just I think you're right. There is a lot more data sets that are collected. Right, these are from observational studies, right? We collect a lot of data in the world now, just trying to observe the world without manipulating it in any way. So this is one way to do it. I mean, there are other, like Judy of Pearl has a whole other separate framework for establishing causality, using, that I have some problems with, but I like this approach because it is rooted in why the RCT gets there, right? So rooted is like, it's a missing data problem. We handle the missing data through a randomization. When we can't do that, we're handling the missing data through models, statistical models to predict that, right? To me, that seems pretty natural step. Obviously you're compromising them. And so I think one of the reasons why in my world, education, social sciences, what we have now, so the Department of Ed, you have TIMS, which is Trends in Math and Science Scale, or which is a large scale international study. You have PISA, the Program of International Student Assessment, which is really done by OECD, but in the United States, it's done by the Department of Ed. You have NAEP, the National Assessment of Education Progress. You have in the Department of Health, you have all of these biannual national surveys they do. You have the census, or the long form census, which has a lot of these variables. They're just observing what's going on in the world. But if you can find that, I want to know the difference between this and, take for example, people have used this procedure to understand the effects of time zone changes, right? Because you could exploit both, whether or not somebody lives on one side or the other in Arizona and Mexico. Is that where like Arizona doesn't change their clock or things like that, right? So it's trying to find these things where you can't otherwise, just do an RCT. And there's just a lot more data. Go on Kaggle and, find data sets and you can say, oh, what's the cause of this versus that?
So one of the things you mentioned was identifying variants.
If you can.
Yeah. What's the process used for doing that? If you're going to use this method?
So for where I do mostly educational interventions, there's something called the What Works Clearinghouse, which defines standards for research design studies. And so for our DAX project, for instance, we have to, because it's an IES grant, we have to meet what's called What Works Clearinghouse standards without reservations. So there's like class, you can meet the standards without reservations, with reservations, blah, 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 right? So PSA would meet the standards with reservations because you're making, in order to meet without, you have to have an RCT, a very strict RCT, low attrition, a whole bunch of other things. Okay, point being, they also outline when you do that, you need to show baseline equivalence. And there's 6 major categories. And then they give you lots of examples of variables that fit in those categories. So things like, I can't remember them all off the top of my head, but like ethnicity and race, right? Sex is one, social economic status is one. I can't remember. Angela's on, she might be able to chime in and say, I can't remember what they all are, but if you just Google What Works Clearinghouse Standards, baseline equivalence, it'll get a list of the variables. So that for me, that's where I start. But I remember early in my dissertation work, my advisor said, okay, you want to know the effects of charter schools and versus traditional public school students. What would you want? What do you think? What does the literature tell us should be predictors of whether or not somebody chooses to be in one of those groups and or is a predictor of the outcome? Because you kind of want to adjust for both, even though you're adjusting it through the treatment place. So you kind of got to know your literature. You got to know your domain. Other questions? I'm looking online.
I have a question.
Hard to tell who fell asleep here.
Everybody's turned around. How does certification differ when you know your treatment groups versus when you don't? So for example, let's say you're doing Alzheimer's treatment, right? And so you may have a receptor and then like a cosin to bind to it, and you have 3 different groups, like a control receptor, control cosin, like a treatment. How does it differ from yours where you're looking to see like if it's a predictor? Versus mine, I would say, I have a prediction in mind. How would stratification differ? Would the code just stratify the data based on the treatment groups that I already have in?
So
it's unnecessary?
Are you asking, you have more than one treatment?
Yes.
Okay, so that's one of the things I blew apart. So we can chat afterwards. So this is a package I wrote called TriMatch, where I have a control and 2 different treatments. And so the kind of setup is the same, somewhat the same. So here I have control units, and I have individuals that receive treatment 1 and those who receive treatment 2. In essence, what I do is estimate 3 different propensity score models. So I take control and treatment 2 individuals, they get propensity scores on this side. I get propensity scores between control and treatment 1, and then treatment 1 and treatment 2. And then what the algorithm does is kind of iteratively go through and says, well, let me find a match here in the traditional way you would do matching with just treatment 1 or treatment 2 and control, I guess. Then, okay, so I found a match in, so what I do is I take the treatment 2, individual, right? So they have a propensity score of this and this one. right? They would have a propensity score in this model as well, right? So treatment 2, I have 2 propensity scores, one in this model and one in this model. So if I say, okay, here's my control, I match to this treatment person who was in treatment 2, well, they appear over here in this model. So I find a treatment 1 match that is close, right? And then they also appear over here. And then I look to see, okay, well, then this control, so this is a matched triplet. But the key here is the algorithm is trying to minimize the distance between the propensity score across these 3 models. So it does it iteratively. So then what you come out with is a matched triplet. So I find an individual in the control that is similar to somebody in treatment 1, that is similar to someone in treatment 2. So that's one approach. Theoretically, I thought about extending this to 4 groups. It could be 2 controls in a treat. It doesn't, but that's kind of how I designed it. There is another paper, can't remember off the top of my head, I could send you, where somebody defined a model if you have a continuous treatment, meaning it's like a dosage or something like, right? So you have control that gets nothing, and then maybe you have 10, 20, 30, 40 milligrams, right? This would be more common in the medical world. So they have a different approach to estimating the propensity scores. But if you just have discrete groups, this is the one way you could do it. Does that answer your question?
It does. It's a lot, but it does. I get it.
You can reach out. I could chat more about it, but this is sort of a quick principle on how that works. So this is a funny story because I developed this method because I was trying to, when I was in institutional research, I was working with a dean who was they were doing this intensive outreach with academic advisors and new onboarding students. And they had a small number, like 2 advisors, and they had a very small number of students, right? So they could really have a high touch. And they wanted, she's like, okay, this should help, right? This should help. And I'm looking at the data, and I'm like, it's not doing anything. And so I'm like, well, these 2 people are different, right? So the intervention is not really the same. It's like advisor A has one intervention, advisor B has a different way of approaching students. And it turned out advisor A had really high retention rates, and advisor B actually had negative retention, right? Or very much lower. Actually, it could have been negative, but lower retention rates, right? And it turns out that person wasn't doing a very good job, right? And they ended up getting transferred, and that wasn't a job for them. But there was some selection bias in the process of where students ended up. So I couldn't just do a straight comparison because there were systematic differences between the students. And so I did this, and it's like, okay. And then I ended up using it in another study where I wanted to look at the impact of tutoring. And in that case, what I looked at is students who use tutoring services once in a semester versus 2 or more times. So I wanted to know, is there an additive effect? In fact, I think that's what, and if you want the punchline, the answer is yes, but it's not as big as I thought. So this is, right, so the effect size is 0.3 for students who use tutoring services once in the semester. And actually, no, I guess it was, right? So it doubled. Students who used it 2 or more times had an effect size of 0.62. And then this is the difference between treatment and treatment. Unfortunately, it's negative, meaning treatment, it's just the way that I subtracted treatment 2 from treatment 1. Right? People who use it 2 or more times did better. It's just an orientation at the bottom, but I should fix that. It's a little weird looking at. But anyways, and then I used it in this one because I couldn't publish the other one because the results were too embarrassing. So they wouldn't let me do it. So I found another place to use it. But that's another thing you need to think about when you develop interventions. Like when I'm going back to the Head Start, we often get said the intervention was Melinda, was her name. She was a director who was like in the Head Start every day, working with teachers and families, and then when we try to replicate it to another school, they weren't getting the same any effects, right? It's like, well, the intervention isn't PBIS, it's Melinda. And that's kind of what we saw, right? When you have an intervention that relies on human beings doing that intervention, sometimes it's hard to tease out the intervention from the people doing it. That's another kind of side.
Did she go undergo some sort of professional training, or just something inherent?
Oh, I think it was inherent with her. Yeah.
People just have it.
Some people just, she was just an amazing human being. She's like one of those people you meet in the context. You're like, yeah, she's gonna do good stuff. Yeah, so, short of cloning her, I don't know if there's really anything you could do.
That's not legal.
No, it's not legal. All right. Oh, thanks, Angela. Any questions online? Otherwise, I am going to stop the recording. I could have stopped screen sharing. All right. Yeah. Let's see.